Okay, so this is going to be a condensed review of everything relating to the solutions unit. So a couple of things that we need to start with before we even talk about solutions are some unusual properties about water. The bonds between H and O inside a water molecule are polar covalent. So remember, if I were to draw the structure of water, I've got oxygen with its 6 valence electrons, and then H comes in and bonds on this side, and H comes in and bonds on this side. And remember that we determine if something is polar or not by two things: electronegativity difference and whether the molecule is symmetrical or not. Well, right away we can see this molecule is not symmetrical, so that leads us to believe that it is polar. And we know that oxygen has a higher electronegativity value than hydrogen, as evidenced in Table S in the electronegativity column. So the oxygen side of the water molecule becomes slightly negative, while the hydrogen side slightly positive. There's an unequal distribution of charge. Water is also unique in that it exhibits what's called hydrogen bonds between its molecules. Hydrogen bonds are a very strong bond, and they occur in a molecule when hydrogen bonds to NOF, nitrogen, oxygen, and fluorine. So when I have any of those elements with H, that's considered hydrogen bond. And therefore very strong. As a result of this hydrogen bonding, water has an unusually high melting point and boiling point. And that's also similar to other molecules like H2S, because sulfur is in the same group as oxygen and therefore would behave similarly due to the same number of valence electrons. Water also has a very high specific heat. We can find this in Table B. It is 4.18 joules per gram, and we use this value when we're calculating heat problems. And water solutions contain ions capable of conducting electricity. The substances that form the ions in solution are called electrolytes. And in our last review in class, we mentioned that electrolytes have the ability to conduct electricity when they are in the aqueous state, and this includes acids, bases, and salts. Remember, an acid starts with H. Just to review that. Acids start with H, or if it's an organic acid, end in COOH, and one of those O's is a double bond. Bases, generally speaking, are a metal plus OH, and we can find those in Table L, and the exception to the Arrhenius base rule is NH3. And lastly, salts. Salts generally contain ionic bonds. So this can be a metal and a non-metal. Specifically, we usually see this with a halogen. It can be a metal and a polyatomic. I'm just going to write poly. Or it can be two polys. So that's how you recognize an electrolyte. Okay. Second point, water is able to make solutions with many substances. Solutions are always homogeneous. This is important. All solutions are homogeneous. Water will dissolve many ionic compounds, and it will also dissolve molecular substances if they are polar. That reminds us of like dissolves like. So when we think about like dissolves like, polar dissolves polar, polar dissolves ionic, nonpolar dissolves nonpolar. So on the reagents, if they say that benzene will not dissolve in water, and they ask you why in terms of polarity, you don't have to know what benzene is. You already know that water is polar, and if something doesn't dissolve in water, it's because it must be nonpolar. Acids dissolve in water to form H ions, and bases dissolve in water to form OH minus. And what this is just saying is that if I have HCl and I put it in water, I'm going to get H plus and Cl minus. If I put NaOH in water, I'm going to get Na plus and OH minus. This is one of the reasons why acids and bases are electrolytes, because they have mobile charge. In order to conduct, I need mobile charge. And the same with salts. If I put NaCl and I put it in water, so it's aqueous, I have Na plus and Cl minus. Once again, mobile charge. Okay, I've already gone over table F, but I will review it one more because it is considered part of the solutions unit. We use table F to determine whether something is soluble or insoluble. And when we say insoluble, we usually refer to the fact that it forms a precipitate. Precipitate is that sludge that you get on the bottom of a test tube when you mix two things together, and one of them is insoluble in the other. So very briefly, the left side of the table are ions that are soluble, unless they meet one of the exceptions, and then the opposite happens. The right side of the table are ions that are insoluble, unless you meet one of the exceptions, and then the opposite will happen. So let's take a few of these examples. We go to the last part of the name, nitrates. You can see that nitrates are on the soluble side and there are no exceptions, so this is soluble. Silver chloride, I find chlorides. Chlorides are listed under halides. They are soluble unless combined with silver, lead, or mercury. I have met that exception. That means the opposite happens, and this is insoluble. Barium sulfate. Sulfates are soluble unless combined with silver, calcium, strontium, barium, there it is, and lead. So the opposite will happen, and this is insoluble. Potassium hydroxide. Hydroxides are insoluble unless combined with, this should say group 1 over here, calcium, barium, strontium, or ammonium. Well, magnesium is a group 2, so that is going to remain insoluble because I don't, potassium. My bad. Potassium is group 1, so the opposite will happen and this will be soluble. The magnesiums with the sulfide. Sulfides. Where are my sulfides? Sulfides are on the insoluble side unless combined with group 1 or ammonium, and magnesium is group 2, so it's going to remain insoluble. And the last one, ammonium carbonate. Carbonates are on the insoluble side unless combined with group 1 or ammonium, and ammonium is NH4, so the opposite happens, and this is soluble. So there's a quick review of table F. Solubility describes how much of a particular solute, okay, that's the thing being dissolved. So that is the iced tea powder. in a set amount of water, and water is referred to as our solvent, okay, the thing doing the dissolving, at a certain temperature. We're going to use table G. This table uses 100 grams of water. So if you're given anything other than 100 grams of water, you have to set up a proportion so that you can make adjustments for either more water or less water. Saturated solutions hold all the solute possible at the temperature chosen for the water. An increase in temperature of the water usually makes it capable of dissolving more solute. So think of a glass of water. If you want to dissolve sugar in water, if you have cold water versus warm water, you're going to be able to dissolve more in the warm water. That's what this is saying. Now, generally speaking, as we increase temperature of the water, we can increase the amount of solute that dissolves. However, this is not true for gases. As we increase the temperature of a gas, the amount of solute we can dissolve decreases. And lastly, an increase in pressure over the solution increases the solubility of gas solutes. It does not have an effect on the solubility of solutes that are liquids or solids. One of the questions on the Regents a couple years ago says, what will happen if I increase the pressure on KNO3 solid? And nothing happens to the solubility because it is a solid. If it were a gas, then it would increase it. That's how we get CO2 into soda. We force the CO2 gas into the liquid because CO2 is a gas, therefore increasing pressure increases its solubility. So let's look at some standard Table G questions. Remember, first of all, that if my data point is right on the line, then this would be saturated. I always like to say I sat on the line. If my data point, if I'm looking at the NaNO3 line and my data point is below the line, okay, then I say that I am unsaturated. And if my data point is above the line, in this case the NaNO3 line in question, then I say that the substance is supersaturated. Okay, so I'm going to erase this so that we can start with a clean graph and answer some practice questions here. Okay, so what is the saturation of 5 grams of SO2 at 50 degrees? So I'm going to go to 50 degrees and see where that 5 grams is. So 5 grams, 50 degrees, my data point is right on the line. So for number 1, this is saturated. And might I point out before we continue that most of the lines have a positive slope. These are solids, and as we increase the temperature, their solubility increases. We do have 3 lines, however, that have a negative slope. That would be HCl, NH3, and SO2. That's because these are gases, and as we increase the temperature, the solubility of the gas decreases. Question 2. What is the saturation of 30 grams of KCl at 30 degrees? So I go to 30 degrees, and they're asking for the saturation, and I see where that is going to intersect the KCl line. I put a dot, and I go over and I read what this is. and it looks like it's just about half, maybe a little bit more. So I would say about 35 or 36 grams. Don't ever put a range, pick one or the other, but try to be as exact as possible. The Regents usually only gives you a 1 or 2 gram variance, plus or minus. Oh, I completely messed up that question. Okay, what is the saturation of 30 grams of KCl at 30 degrees? Okay, so what is the saturation of 30 grams of KCl at 30 degrees? So I go to 30 degrees, 30 grams, and I'm going to put a dot. Okay, this was question 1. I'll label this. This is question 2. So let's look where I am in relation to KCl. I'm below the line, so this is unsaturated. Number 3. What is the saturation of 90 grams of NaNO3 at 20 degrees? I'm going to go to 20 degrees, 90 grams, and I'm going to put a dot. This is question 3. NaNO3, I am just above that line, just above it, so that makes me supersaturated. What mass of HCl is needed to make a saturated solution at 60 degrees? So I'm going to go to 60 degrees. It has to be saturated, so it has to be right on the HCl line. So there's my point. And I'm going to go across and I'm going to read the grams on that, and that's about 55 grams. So I went to 60 degrees, they wanted it to be saturated, and I saw where it intersected HCl and read the grams. What mass of NH3 is needed to make a saturated solution at 20 degrees? So 20 degrees, NH3, saturated, it's going to be right on the line, so that is going to also be 55 grams. Six, at what temperature would 40 grams of NaCl make a saturated solution? So they're telling us that we have 40 grams. That's this line. And NaCl. So I have to go over and see where this intersects the NaCl line, which is probably right about here. Because it's got to be on the line. 40 grams on the line, and I go down and I read this temperature, and that's about 84 degrees. It's about 84 degrees. At what temperature would 140 grams of Ki make a saturated solution? 140 grams, and I'm going to find where it intersects Ki, which is right there, and I'm going to go down and I'm going to read that temperature, and that is 15 degrees Celsius. And the last question. If I have 120 grams of KNO3 at 65, so where are we? 120 KNO3. So I have 120 grams of KNO3. I'm just going to write this down over here. So 120 grams. I'm going to cool it to 50 degrees. So I have to see 50 degrees where it intersects KNO3. Right here. So at 50 degrees, it can only hold about 83 grams. So at 50 degrees, it can hold 83 grams. They want to know what mass settles out. Well, I started with 120, I cooled it to 50, now it can only hold 83. So 120 minus 83 is going to be 37 grams settles out. Okay, so that's a review of the solubility curves table. Let's move along to some math that you have to know for this unit. Things that you should know that describe solutions and concentrations are molarity, percent mass, and parts per million. So I'm going to do a couple problems in each of those. Remember that molarity is equal to moles over liters. And depending on what you're given in a problem, you may have to do a two-step problem. If you don't have all of the variables that you need to outright solve the molarity problem, you may have to use your mole calculation, which is moles given mass over GFM. So 2 moles of NH3 in 5 liters is what molarity. So if we substitute in molarity equals moles over liters, remember always put the 1 here because then you have the proportion set up. So you're trying to find molarity, so X equals 2 over 5. And here's a 1. So you basically have 5x equals 2. And then you divide both sides by 5. And you get your molarity of 0.4. Let's not forget units. Again, I'm going to use this same setup right here. 3 moles, so I've got x over 1 equals 3 over 8. Therefore, I have 8x equal to 3. I divide both sides by 8. Wow, that didn't come out like an 8. And I get 0.375, which you can round to 0.38 is fine. Now the next one, 20 grams of NaOH in a 2-liter solution. So if my formula is molarity equals moles over liters, I can see that I don't have moles. I have my liters. So I have to do a mole calculation formula first. So I'm going to set up what I do know. X equals, I don't know my moles, 2. So I got to get my moles. So let's do a moles equals given mass over GFM first. Remember, I'm going to put a 1 here so my proportion is set up. And I've got x over 1 equals 20. And then I need the GFM of NaOH. Well, I go to my periodic table. I know that Na is 23, oxygen is 16, and H is 1. So that's a total of 40. So here when I solve for x, I'm going to get 20 divided by 40, which is going to be 0.5. So that's 0.5 moles. That's not my answer. Now I can go over here, put 0.5 in. So I have 2x equals 0.5. 0.5 divided by 2 is going to be 0.25. So 0.25 molar is my final answer. That's a big M. Let's do one more of those. Down here, I'm going to have x over 1 equals, I don't know my moles, over 0.5 liters. So again, I have to do my mole formula. So I'm going to do my moles over 1 equals given mass over GFM. So that's going to be X over 1 equals 87 over, and I need the GFM of NaCl, so we know that Na is 23, and Cl is 35.5. So that's going to give me 58.5. So 87 divided by that is going to give me 1.49. So I've got 1.49 moles. And then I put 1.49 moles here. And when I cross multiply and solve for x, I get 2.97, or close to 3 molar. Okay, so there's your molarity. It's either going to be a single step if you've been given all the variables that you need, or it could be a two-step problem where you have to find your moles first using the mole formula and then substitute that into the molarity formula. Next we have percent composition, which you know is part over whole times 100. Now normally we do something like, let me do a harder one, BaCl2 dot 2H2O. Remember that this dot means with, it does not mean multiply. So this is barium chloride with 2 water molecules. It's a hydrated crystal. So if I asked you what was the percent of water in the barium chloride dihydrate, you would realize that, let me change my ink color, that this is the part, because I said percent of water in the whole thing. This is my whole thing. So water, 16 plus 2 hydrogens is 18. That's the mass of 1 water times 2 is 36. So my part is 36. My whole is going to be that 36 plus the barium chloride. So chlorine is 35.5, and there's 2 of them. So that's going to give me 71, plus the barium is 137. So that's going to be 208. So I actually have 36 divided by 36 plus 208, because that's the whole thing, times 100. And that's going to give me 14.75%. Now, that's straight percent comp. Sometimes they mess it up a little, mix it up a little, I guess is a better word, and they say 25 grams of NaCl in a 100-gram solution. So in this case, my part is this, and my whole is the whole thing. So this would be 25 over 125 times 100. And that's going to be 20%. 25 grams of NaCl, it's the same one, did that one. Okay, 76 mils of O2 in 140 ml solution. So now they just changed it from grams to volume. It's going to be the same thing. This is going to be 76 over my whole, because the 76 in 140 mils, we need the whole solution, is going to be 76 plus 140 times 100. And that's going to give me 35.2%. Okay, and the last one, 225 milliliters in 1 liter. You're not going to get one like this, but remember, You can go from milliliters to liters or liters to milliliters if you know kids hate doing math during cold months. And this is your baseline, liter, meter, gram. If I'm going from milliliters to liters, that's 1, 2, 3 places to the left. 1, 2, 3. So that's 0.225 liters. So that's going to be my part, 0.225 liters over the whole thing, 0.225 plus 1 times 100. And that's going to give me 18.4%. And you can pause me at any time to go back and do your own calculations. Okay. Now we're going to do parts per million. Parts per million is a concentration formula that measures very small amounts of solute. So this is the mass of the solute over the mass of the solution times a million, which is 10 to the 6. Now, for most of you, it's very easy to solve this if you're just finding parts per million. So here I have 0.025 grams in a 125 gram sample. So my parts per million, here is my 0.025 solute over the mass of the whole thing. So it's going to be 0.025 plus 125 times 10 to the 6. And make sure that you're using parentheses. I'd hate to see you set up a problem and then get it wrong. So if you have to do it in multiple steps, that's fine. So I get 199.96, so this is about 200 ppm. On the next one, milligrams and grams, right away, that's a problem. So go back to kids hate doing math during cold months. Meter, liter, gram. At milligrams, I need to go to grams. 1, 2, 3, 3 places to the left. So that's 1, 2, 3. So this is going to be 0.0035 grams over the whole thing, 0.0035 plus 100 times 10 to the 6th. And you get 34.99, which is 35 parts per million. All right. On the right side here, I've mixed it up. I've given you the grams and samples. 250 gram sample contains 8 parts per million. We want to know what the mass of the solution is. We are trying to find the denominator. So let's set this up. We have 8 ppm equals 250. Oops, sorry. We're trying to find the numerator. My bad. The sample is the whole thing. X over 250 times 10 to the 6th. Remember PEMDAS. Do we have any parentheses? No. Do we have any exponents? No. Do we have multiplication? Yes. What is the opposite of multiplication? As soon as you have a problem set up in this form, you want to divide by whatever it is that you're multiplying by. So divide both sides by 10 to the 6th. These cancel. Now you can simply cross multiply and divide. So I'm going to do this down here. So you have 250 times 8, which is 2,000. So you've got 2,000 equals 10 to the 6th x. Cross multiply and divide. Divide both sides by 10 to the 6th. Therefore, x equals 0.002 grams. So that's our answer to this one. All right, I have 25 parts per million. I'm finding x. My whole sample is 330 times 10 to the 6th. First thing I want to do, get rid of this multiplication, divide both sides by 10 to the 6th. These cancel. So 330 times 25 is 8250 equals 10 to the 6th x. Divide both sides by 10 to the 6th. And I get 0.00825. 0.00825 grams. And that is my answer. Okay, almost done. Solutions having a lower freezing point and a higher boiling point than pure water. This should be then. This effect becomes larger with more concentrated solutions. So what that means is, if I have NaCl, MgCl2, C6H12O6, remember I have to look at the number of pieces. Anything that is covalent does not separate in water, it simply dissolves. So this counts as one piece or one unit. MgCl2 separates into one Mg and two Cls. Therefore, that is 3 pieces. NaCl separates into Na and Cl, which is 2 pieces. So this one will have the greatest effect. It will raise the boiling point and depress the freezing point the most because it has the most ions in solution. Now, if I'm given the same substance, NaCl 1 molar, NaCl 2 molar, and NaCl 0.5 molar, this solution will have the greatest effect because it has more concentration. So there are 2 ways to look at how freezing point and boiling point are affected: the number of pieces and the concentration. But you have to remember anything covalent is always going to be 1 piece. Alright, we're going to do a couple of practice problems from the topic review, and that's going to wrap it up for this crash lesson on solutions. Compared to a 2 molar aqueous solution of NaCl, a 3 molar aqueous solution of NaCl does what? Well, this is more concentration, so it is going to have a higher boiling point and a lower freezing point. It's going to do the most work. Here we have an equilibrium equation, and it wants you to draw 2 water molecules in the box showing the correct orientation of each water molecule toward the Cl ion. So what you're given on the reagents is you're given a box like this, and you're given Cl minus in the middle, and they tell you that this represents H and this represents the O, and they want you to draw two water molecules. So first of all, you know that H2O, you have to formulate what a molecule would look at like. So you've got one O and you've got two H's. Okay. They want you to draw two water molecules, so that's important that we remember that. And we also have to remember that water is polar. So the side with the higher electronegativity pulls the electrons more and has the negative charge. So this side is slightly negative, this side is slightly positive. So once we remember what the charges are, we then have to remember that like charges repel, opposites attract. So my H's are going to be close to my Cl because that is the positive side of the molecule. See? We'll draw two of them because they want two water molecules. There you go. That's what it would look like. Next question. An aqueous solution has 0.007 grams of oxygen dissolved in 1,000 grams of water. Calculate the dissolved oxygen concentration in parts per million. So they want a correct numerical setup and a calculated result. So ppm equals grams of solute over grams of solution times 10 to the 6th. So my solute is 0.0070 grams. That's in 1,000, so I have to add it to it to make the whole solution times 10 to the 6th. So I get 6.99, which is approximately 7 parts per million. Now, I want to state something, because this was an actual Regents question a couple of years and a lot of kids got it wrong. If you leave this, the solute, out of the solution, you forget that it's part of the solution, you're not going to get this question right. You'll still come out with 7 parts per million as your answer, but they won't give you the point because you only had 1,000 in your denominator. So it's very important that grams of solution, you know that that includes the solute plus the solvent. All right, next question. Give us all this. I'm just going to go right to the question. Identify the class of organic compounds to which 1,2-ethanediol belongs to. Well, as soon as I see numbers and I see ethane, I should be thinking organic chemistry. I'm going to go right to my table R, and I'm going to look in my example column for anything that ends in OL, and I see that my OL ending belongs to a class of compounds called alcohols. State in terms of molecular polarity why 1,2-ethanediol is soluble in water. So we know that water is polar. Therefore, 1,2-ethanediol has a similar polarity. Because we know that like dissolves like. Okay. An aqueous solution contains 300 parts per million. Determine the grams of KOH present in 1,000 grams of this solution. So here's my ppm. Here's my grams of solution. So ppm equals grams of mass. Mass of solute over mass of solution times 10 to the 6th. You should get in the habit of writing everything down. 300 equals x over 1,000 times 10 to the 6th. First thing I want to do is get rid of this multiplication, divide both sides by 10 to the 6th. So I'm going to have 300 times 1,000, and then I'm going to divide that by 10 to the 6th, and I'm going to get 0.3 grams as my answer. Okay, that's it. I do want to say something. If you get a percent comp problem, which is part over whole times 100, building off of the last problem I just showed you, say they give you the percent comp, 25% equals, and you're trying to find the whole. And I say, I don't know, 16 grams, and you have x times 100. This is your percent comp. Again, you have multiplication. Simply divide both sides by 100, and you are set up to cross, multiply, and divide. Please do not forget that on those types of problems. All right, that's it.